Hi, I want to talk about a new way of thinking about Newton's second law, and it leads to the discovery of a new term that we call work and the work-energy theory. So, to start with, we could express Newton's laws as we do in chapter 5, where if we limit ourselves to thinking about one direction, the net force in the x direction, let's say it could be a function of x, just in case, well, that would have to equal the mass times our acceleration in the x direction. Well, the acceleration in the x direction from kinematics is just the derivative of velocity with respect to time. So let's play a game called Fun with Math. So fun with math means we're going to just multiply a term into this equation. I'm going to take everything and multiply by the velocity in the x direction. So, if I wanted to then, I could take a closer look to say, alright, well my force in the x direction times my velocity in the x direction would be my force in the x direction, which I said is still a function of x, times velocity is my change in x with respect to time. And that would equal mass times velocity times the derivative of velocity with respect to time. So let's multiply by this differential element dt. Well, if we do that, then dt cancels on the two sides of our equation, so we have our force in the x direction as a function of x times differential element dx, and then we'd have m times our velocity in the x direction times the differential element of the velocity in the x direction. So if we integrate both sides, we'd have the integral of force with respect to position, and we'd have the integral of mass times velocity with respect to velocity. Well, the integral of v dv gives me 1/2 v squared. So if I go from my initial condition to my final condition, I would have a term equal to 1/2 times the mass of my object times its final velocity in the x direction squared minus 1/2 times the mass times the initial velocity in the x direction squared. And this quantity right here is what we call the kinetic energy in physics, or rather the translational kinetic energy. And translational motion just means that the center of mass of an object is moving from one place to another. You're changing its location. So this side is the change in kinetic energy. Now the other side, the integral of our force with respect to x from our starting position to our final position, is what we in physics call the work. So what this says is the work done equals the change in kinetic energy. And this is kind of further proof that physicists are very boring with naming things. Really, the work-energy theory at its core tells us the total work done on an object changes the kinetic energy. Now, there are a few more interesting pieces from this. One of the neat things about this operation, if we instead of thinking about the net force, we think about each force individually, well, the integral of the result of a sum would be equal to the sum of the integrals of the individual components. So just like forces obey a rule of superposition, work obeys a rule of superposition. So we could separate out work into each component. So we could just think about this as the component of work in the x direction. So if we wanted the component of work in the y direction, everywhere I see an x, I'd replace it with a y. So any force that I have that changes in the y direction, changes like y, would be integrated with respect to y, and that would change my kinetic energy in the y direction. And the same thing with z. So if we put it all together then, our total work, and what we can do is use some bookkeeping from vectors in order to simplify writing all three of those equations. We could think about this rather than being just a force with a specific direction element, we could take the dot product of our force with respect to the differential element dr. And the differential element dr is just simply dx in the x direction, dy in the y direction, and dz in the z direction. So with the dot product, I take my x component of force, integrate it with respect to x. I take my y component of force, integrate it with respect to y, z component of force, integrate it with respect to z, add all of those three integrals up to give me my total work, and that would be equal to 1/2 times the mass times my final velocity squared, and that final velocity is just the final velocity dotted with the final velocity to get v final squared. So that would be our x component squared plus our y component squared plus our z component squared. And this initial velocity squared would be v initial dotted with v initial. So the total work done in all directions combined can change the total amount of motion of an object. And later, as we start talking about potential energy and conservative forces, we'll talk about other ways that we could split up the total amount of work into different functional groups, where different sets of forces are doing work for specific reasons. But I'd like to end by just doing a little bit of study for a question that shows up on just about every driver's ed exam, at least in the United States, in every state that I've ever had to test in. And usually one of three things will happen. You've either answered enough questions and you can't get enough questions incorrect, so the system ends your test because it's impossible for you to fail at that point. Or the flip side of that is you can't answer enough correct questions and then it kicks you out because you can't pass. But normally, somewhere along the way, you'll be asked a question like, at 20 miles per hour, your car stops in 15 feet. How far will it take to stop from 60 miles per hour? Essentially implying that the car has the exact same amount of braking force. Well, this question is work energy in action. So if you stop your car, then your final kinetic energy is 0, and your initial kinetic energy would just be 1/2 times the mass of your car times the initial speed squared. Now, on the work side of the equation, the work is the force that's being done braking times the distance. Well, if the force is constant, 1/2's a constant, the mass of your car is constant, the braking distance goes like the speed squared. So, hopefully taking a look at these answers, you're able to rule out 15 feet and 3 feet. The faster you go, your car doesn't stop in the same amount of distance or even less amount of distance. The most commonly chosen answer, though, is what I wrote as C, not because most people guess C when they're unsure, but most people look at it and say, oh, I've gone from 20 miles per hour to 60 miles per hour, that's 3 times faster, I should go 3 times farther. But it's not 45, it's 135 feet. Because distance doesn't go like speed, distance goes like speed squared. So if I have 3 times the speed, 3 squared means I get 9 times the distance. So it goes from 15 feet to 135 feet. Which is why in driving we always say the faster you go, the farther your gap should be between the car in front of you to handle the effect of your reaction time in being able to safely stop. Thanks for watching.